Hi, everybody, and welcome to the Python section of a Bayesian approach to linear mixed models. My name is Eduardo Coronado, and I'm a data scientist soon to join a consulting firm, and I recently graduated from Duke University with a master's in statistics. So just to give you a brief overview of what the goals of this online tutorial are, is to go through a more detailed explanation of the code that I cover in the article of the same name. And in here, I will show you how to implement a Bayesian linear mixed model and do some very basic diagnostics on whether the Markov chains, which are used in Bayesian inference, show any troubles or flags that you should be aware of. The more anything related to model checking or model evaluation is something that I will cover in a subsequent article, so you will not find that in this tutorial. Just to give you a brief context, the dataset that we'll be using is one of simulated website bounce rates, which I will show you in a second. First, let's load all of the libraries that we need. Here we will use our traditional pandas, numpy, pyplot, as well as PyMC3, which is the one that we will use to do the Bayesian inference. And so when we load the data and we look at it, our response variable is bounce time, which is in seconds. We have a predictor, age, and a grouping variable, county. There are a total of 8 counties in this data set, so 8 different groups. So to start this tutorial, I will center scale the age variable and call it std age. And as you can see, that means that the mean is going to be practically 0, and then the variance is just going to be 1. That's what I'm doing, and it helps with interpretation of the variables later on, which I'll cover in a subsequent article. So let's first dive into an EDA in the modeling process. This is normally the first step, and I just want you to keep in mind that this shouldn't just be, I want to plot some data and see some relationships between my variables or my predictors. Although this is a very useful exercise, you should think about it more extensively as an iterative tool in your modeling process, in which it can help you see whether the models that you're thinking on building make sense and can capture the different aspects of your data. So I normally suggest you start with a simple model. In our case, we can fit a simple linear regression. That's the simplest model we can use with a continuous response variable. We will use the scikit-learn linear regression to fit this model. And then I'll use Plotly's Plotly express scatter function, which makes it super easy to plot this type of data. I like Plotly or experiment with Plotly just because it's a nice way to make it interactive. And so as you can see, we have the population kind of like trend line, in which is in black, and we see each one of the individual groups or counties are color coded differently. However, once we plot this kind of like initial base simple linear regression, we see that maybe some of this, counties might not follow that trend line, specifically not the slope or the effect that age is having with bounce time, especially on these ones down here or up here. So what we could do is we could see how this looks like if we fit individual, trend lines as what would be a mixed effects model, so a more complex model. So we are building up from a simple linear regression to a more complex. So in here we can see with Plotly Express, we can plot the same now using actually the flag called trendline OLS. It allows you to fit individual lines. This is not particularly a mixed effects model because this is equivalently to a no pool model, but it kind of like does the trick, in which we can see now that, for example, the individual group lines don't really seem to resemble this initial population trend line, which shows an example of Simpson's paradox, which basically explains what I just said. The individual trend, when we ignore the groupings, we might get a very different trend for the data. And so we can see kind of like clearly from here that there seems to be varying intercepts. These ones are kind of low, these are high, but maybe we might want to check also some varying slopes. I will not fit those in this in this demo, but you can think about it as something you might want to look into as one of the models you want to compare later on. You can do the same using Seaborn if you're more familiar with it. You can use the LM plot to pretty much plot these individual trend lines with the standard errors. So it's pretty much the same plot that I showed before. Okay, so if you're not very familiar with Bayesian modeling, or if you are, you know that one of the biggest challenges is how do I choose the priors that I'll be using for my inferences? And a lot of the times that kind of like shies people away from approaching these models just because they don't know how to go ahead and tackle it. And there's actually a very useful tool that you can use to make this more approachable. And it's basically simulating data with your priors, which in this case is called prior predictive checks. So what do I mean by that? I basically mean, as I just mentioned, is you just set up what your model might look like. So in this example, I'm getting a random intercept model. So here I'm just getting my observed data, the actual indices or like individual codes for the counties rather than like having it as a strings. And then I'm just starting or initializing a data frame, a pandas data frame. And just for reproducibility, I will be setting a seed at each iteration. I'm going to be iterating 20 different data sets. You can think this as a flip book of data sets. And the whole idea of here is you want to see whether your priors can generate plausible values for a data set. So as an example, does the priors produce bounce rates that range up to maybe like 700 seconds versus like implausible data sets, which might be 10,000 seconds. That might not be very real or very plausible value if you were to collect data from website bounce rates. So that's what it means by doing prior predictive checks, is for you to generate data such that it actually makes sense given your context, rather than just using generic weakly informative priors, which basically means I put a lot of mass in the tails just because I'm very unsure of where I should center the distribution I'm using. So, but that could be at the expense that you might get in plausible data sets. So in here, basically what I'm doing is I'm getting a prior for the group specific variance. This is tau 0. I'm getting the population noise, which is sigma. I'm getting a random intercept for each individual county, where I used the just sampled group-specific variance. And I'm also sampling the different fixed effects that I have. And basically, I just create this like kind of like y-hat, if you want to think about it, like an actual set of predictions or simulated data, and then I just store it into that data frame that we just created. So if we run this, we can now actually use, again, Plotly Express to kind of like animate these based on the simulation number that I just used and kind of like see where they fall. So in the y-axis, we can see this is the simulated bounce rates versus like the observed bounce rates on the x-axis. So if we look at some of the simulations, the simulated values are still within a range that seems plausible. Our observed is from maybe like 150 to like 250, and the simulated ones are going from like less than 100 to like greater than 300, which still sounds like reasonable potential data sets. In here, we can click play, and it might show us a different type of data sets. This would change, obviously, if the axis would change, but it's kind of hard to do it with Plotly Express, which is kind of like one of the limitations of this library right now. But this is another key example, is like we can get very small data, but we can also get very large data. So it still makes sense to set up, the priors that I chose here. This is a very experimental procedure, so you should try, to use, to set priors that can simulate data that make sense both in the context that you're using, but also can generate plausible values. So those are the two things. Okay, so now we can go into actually fitting the models. Now that we've kind of like, imagine you've done all this flipbook and you've chosen your priors, you can now move into actually doing the models. So here's where we'll use PyMC3, which runs on Theano. And Theano allows you to fit or do some Bayesian inference based on Hamiltonian Monte Carlo. I won't go into the details, but this is basically I would say the go-to library to fit Bayesian models without having to know the specifics of how to write a stand model like in PyStan or any more complex methods. And it'll soon be replaced by PyMC4, which is still in development, and that's going to be based on TensorFlow. So looking forward to that. So, okay, let's start with a simple linear regression. This is our model. As you can see, that like our data is normally distributed, given some fixed effects and some noise. And I've set up this priors based on the flipbook that I created previously. And if you're fitting a simple linear regression, PyMC3 provides a very nice from formula method, which is pretty nice because you can just create a dictionary with different types of distributions that you want to assign to each one of the parameters. And you can set up the formula such that, like in here, like you would do in R, for example, I'm just saying that this has a slope, and standard age or standardized age is the predictor plus the intercept. So I give it the data, and then I can set up some specific sampler specific controls. I won't go into details, but this says find the maximum a posteriori, which gives you like the posterior mode. And then this is something for like the Hamiltonian Monte Carlo controls. Here I will be sampling 4,000 iterations. Tune is the same as burn-in. And then I'll set up a random seed. I can specify the cores and the chains. And then one thing that is very nice with PyMC3 is it integrates with Arvis, which we will use to do some of the diagnostics later on and plot the data. So to be able to make more elaborate plots, it's very useful to turn your actual sample data that is going to be stored in LR trace into kind of like an Arvis inference data type. And for that, you need to like do some prior samples and some posterior sampling based on your Markov chain samples. And you can store it into this data set. You can look into the Arvis and the PyMC3 documentation for more information on how to set these up. But as you can see, I'm just setting up that model, and it'll take a quick second to start it off and run all the inferences. But in here, it's going to give you some information about the log posterior. It'll tell you about divergences, which we will talk in a second when we get to diagnostics. Basically, if you get 0 divergences, you're good. If you get a certain amount of divergences, it might be problematic, and there's ways to actually check it numerically and visually, which makes it super nice. It's sampling this is creating the posterior dross and storing it in the Arvis inference data type. Okay, so we fit up the simple linear regression, and now we can move on to fitting a random intercept model. In this case, if you've seen the R version of this tutorial, you'll see that BRMS can help you sample in any way. The parametrization sometimes doesn't really matter as much. But when it comes to PyMC3, parametrization is quite key because it's a very explicit sampling library. So in this case, I use a parametrization referred to as a mean-centered parametrization. You can look more into the details of non-centered versus centered parametrizations online in the STAN website. I've linked an example in the article. But the basic idea is we still have a random intercept alpha j, where j is the county, and we have a fixed slope. This random kind of like component takes into account some, it's centered around some mu0, which we can then set a prior that is kind of reflective of our, let's say, population mean. So you can think about it as y bar. So that's a way you can like think about that as a fixed intercept. And then there's some variation across that centered mu0. And of course we have our sigmas. So let's move on. So let's get some of the information from our data frame. And now this is the model that will be fitting. Let me run it while I explain. Basically, again, we use a context manager as before, which I forgot to mention. Apologies for that. But now what we're going to be doing is we're not going to use the formula builder that we used previously. We're going to explicitly sample each and every single one of the components listed here above. So first, we're going to sample our mu0 and tau0. And you can look at all the available distributions in the PyMC3 website, but here I'm setting them according to what I just mentioned here above. Then I'm going to use these two as kind of like the random variables to sample the random intercept. And I want this to have, be one for each of the counties. Then I'm going to sample a fixed slope, and then I'm going to create, I'm going to build up the mean of the distribution of the data, and then I'm going to use that plus some population variance to sample, like let's say the likelihood function of the data. Again, we can use some ways to select where to start the sampler and modify the algorithm that runs this inference. And we use, again, 4,000 iterations, 1,000 for burn-in, which we will be discarding. And then we're going to basically get some prior predictive samples, some posterior predictive samples based on this Rn trace object, which is still available after. And then we're going to build the same RVis inference data type that we will use for later in visualizations. And as I mentioned, you can go online and see how to specify this data type, which can be very useful outside of plotting your traditional trace plot diagnostics or autocorrelation function diagnostics. It'll come in handy. And it'll come in handy in future publications that I will be posting. Okay, so we now fit the data. We see there's no divergences. Just as going back a little bit into this center parametrization, I had originally not used the center parametrization for this sampling. I had originally used the same kind of like sampling that you see here in the prior predictive checks. And it actually was creating a lot of divergences. It was not being very efficient. So that's why, as I mentioned, you might want to reparameterize if you see something like that causing you problems. Okay, but now let's go into like the diagnostics. So turns out that PyMC3 comes with some plots that can help you identify divergences. RVis uses as a backend matplotlib, but it can also use bokeh. which is kind of like a Plotly-like interactive plotting tool if you are not familiar with it. And we can use that to kind of like identify potential divergent transitions, which would come out as neon green in this plot to see if there was any like issues or potentially some of our inferences might not be as reliable as we want. And so just to give you some context is this Hamiltonian Monte Carlo algorithm use the version that PyMC3 uses is the no U-turn sampler, which you can look into the details. But basically, there's an assumption that the posterior is somewhat like smooth, and so you are using some first order gradients to basically define where to take new steps to explore the posterior. And so if you find an area that is non-smooth or has a lot of variability, you might get like deviated from an optimal path that the algorithm has set for the transition. And so that is basically a divergence. And it might tell you that the algorithm will get stuck in an area and maybe wasn't able to explore fully that part that might be related to some of your covariates. And so that is a sticking point in the sense that your chains haven't converged pretty much. And so you might want to go back and run your chains longer or reparameterize to kind of like find ways to be able to explore better that space. So in here, we don't see any green. Basically, there's no divergent transition, so perfect. Pretty much, it gives us the same idea that it came here, but you can imagine if I get like 180, I would like to know exactly where is the issues coming from or which areas. It pretty much divergences gives you like a sense of the geometry of your posterior, which is really nice. So moving forward, as I mentioned, you can use bokeh as a way to plot things in PyMC3. You can import it into your notebook. You need some extensions with Jupyter to be able to plot it in line. But I'm going to plot right now some trace plots. And I'm going to put both chains within the same plots. And you'll see in a quick second how it's like interactive, such as like Plotly. Maybe you might not want this because it doesn't really give you any value, but there might be other plots where it might be convenient to have another backend plotting mechanism. One word of advice, if you're plotting everything with bokeh, it takes a lot of memory. So that's something that you might think about. Your Jupyter notebook might become a couple of megabytes to like, tens of megabytes just by having these plots in the Jupyter notebook. Okay, so then we can also plot the autocorrelation function diagrams, again with a built-in autocore plot method from or function from PyMC3. And we can see that I put a lag of 15, but we can see that the autocorrelation pretty much dies out after lag 1, which follows our theoretical assumptions or the theoretical assumptions of the Markov property, which you can read more about that and Monte Carlo Markov chain Monte Carlo sampling. So I hope this tutorial was useful and provided you with an intuitive way to fit these models in Python. These can be a little challenging and might seem complex at the beginning, but once you start fitting them more regularly and kind of understanding how to do some sampling, you can see that it can be very straightforward. As long as you parameterize or specify everything in a model, you can actually like list it out. And then within the context manager, the very nice thing is the library will take care of everything, and you will get your posterior inferences out of a trace or an Arvis inference data type object. Thank you very much, and feel free to let me know if you have any comments or if you liked it or if you would like me to further explore any of these concepts.